How many of you have wondered what it would be like to be an astronaut in outer space, beyond Earth's gravity, completely weightless? Well, you know what? The astronauts have to wonder about that too. The reason is, when they're in outer space, they are not beyond Earth's gravity. In fact, every object in the universe exerts a gravitational force on every other object in the universe. That is one of the main tenets behind the law of universal gravitation, which is what we are going to learn about in this section. What exactly is gravity? How can it be explained mathematically? How can it be best understood? Another thing you might have heard is that Isaac Newton discovered gravity. Gravity goes back to Galileo's time, and Newton understood the concept of gravity as best understood at that time, which was related to Newton's first and second law. If something is moving and there's no outside force on it, it continues to move. If something undergoes a change in its speed or direction, that means a force, an outside force, is responsible for that. According to legend, he had his eureka moment when an apple fell out of the tree and hit him in the head, and all of a sudden he saw things clearer now after that hit to the head. So what Newton did that was significant was what he understood, that the moon, if there was no outside force on it, would just continue in a straight line, leave its orbit, leave the Earth far behind. But it didn't. It circled the Earth. And the reason was it was falling towards Earth. It was falling beneath where it would be if there was no force of gravity acting on it. Let's look at the next slide to try to get a picture of this. Falling around Earth. Let's take another look at this. So here's the moon, and the red line represents the direction, the path the moon would take if there was no other force on it. It would just continue to go out in that direction at the same velocity forever until another force acts on it. Remember, in space there is no friction. There's nothing slowing the moon down. But what actually happens is the moon ends up taking the dashed green line path because of the pull of Earth's gravity. Still traveling at the same speed, it's just taking a curved path. Now, if we continue this out and we look at it where the moon is, right here, right now, if you take the moon's velocity and there is no force acting on it, it would look something like this and just continue out in that direction. What actually happens is it takes a path like this blue dashed line and will continue on its curved path. If this keeps occurring again and again, which it does, the moon ends up circling the Earth. It doesn't end up spiraling into the Earth because the speed of the moon does not decrease because there's no friction. The only thing that's changing is the direction. The Earth is changing its direction, so it's accelerating. It's falling around, the moon is falling around the Earth. The moon's not going to spiral into it because there's nothing slowing down its speed. The moon is always going to end up closer to Earth than it would be if it took a straight line path due to Earth's gravity. But it's not going to end up being any closer to that because there's nothing slowing it down. So the moon is in effect falling around the Earth. This is one of Newton's original drawings that shows if something has enough speed, if fired from a mountaintop, it could end up falling around Earth indefinitely. It would have to have a certain speed to reach that threshold to become a satellite, but after that it would become an Earth satellite, which is what the moon is, an Earth satellite, something that falls around another body. And again, the reason the moon doesn't fall into the Earth is because of its tangential velocity. It has a high enough tangential velocity that it's going to do a circular orbit and fall around the Earth rather than into it. It has such a high tangential velocity, and there's no resistance that's slowing that speed down. So here you've got a red arrow representing the tangential velocity. Now this is not a force. This represents its velocity, its speed and direction. The only force in this drawing is the pull of gravity due to the Earth, which causes it to take its circular path and fall around Earth. So red arrow just represents the velocity. The only force vector on this drawing is the blue arrow representing the pull of gravity, causing it to take its circular path. This is another slightly more detailed drawing of where the Earth should be if there's no gravity and where it actually is with gravity. So I encourage you to take a few seconds or minutes or however much time you need to study this, think about this, come back to this to try to get a complete picture of what's going on here. Now, this doesn't just apply to the moon going around Earth, but any body in space going around any other. This is the same principle that explains why the Earth goes around the sun. We all fall around the sun once every year. The Earth falls around the sun. Now, just like pretty much everything else in physics, the beauty of this is you can express this in mathematic terms as well. So here we have the law of universal gravitation, which explains mathematically what's going on with one object going around another. And it states that the gravitational force is directly proportional to, now don't write this down in your notes yet, because this is saying it's proportional to, in a couple slides you're actually going to see the formula that shows what gravitational force is equivalent to. But it is proportional to the two masses involved. So if you have the moon and the Earth, mass 1 would be the moon, mass 2 would be the Earth, or vice versa, it doesn't matter. So you have the mass of one object multiplied by the mass of the other object divided by the distance squared. That's something important we're going to come back to. That distance squared means that a big part, something very important to the amount of gravitational force between two objects, is the distance between their two centers of mass. Not between the outer surface, but between the center of mass of the two objects. Here's just a quick slide on the center of mass if you're interested. Here's the formula that is meant to go in your notes when it says, what is the mathematical formula for universal gravitation? The difference is, instead of directly proportional, this tells you exactly what the gravitational force is equal to. It's equal to G, which is a constant that was actually experimentally found. And we will be talking more about that constant when we get to electrical force, but for now it's G. It's a constant that will be given to you. Now it's equal to that constant multiplied by the mass of object 1 and the mass of object 2 divided by the distance between the two masses squared. This is very important. What this means is that, let's say you have 1 over x squared. As x increases, the number that this equals is going to drop exponentially. It's called the inverse square law. The inverse square. Now, this means, let's say I have 1 over 2 squared. Well, that's going to come out to be 1/4. But if I take that 2 and I double it, and I make it 1 over 4 squared, instead of having 1/8, just double, or doubling the denominator, now I've got 1 over 16. So now the distance is doubled, but instead of the force getting twice as weak, it's actually 4 times as weak. And again, this is the inverse square law. Now, the value of G in that equation, G multiplied by mass 1 by mass 2 divided by the distance squared. So it's what we're taking this whole thing and multiplying by. The value of G is 6.67398 times 10 to the negative 11. That's point followed by 10 zeros, 667398. That is not a big number. What this tells us is that the force of gravity is a relatively weak force compared to other forces in the universe. The reason it seems so large to us is due to the fact that one of the masses we're dealing with is usually the Earth. And compared to the other mass we're dealing with, like us, a ball, a house, a car, compared to the Earth has a pretty big mass. So it seems like it's a big force in our everyday lives. But in terms of other forces in the universe, the force of gravity is a relatively weak force. We will talk more about that again in our unit on electricity. The next couple slides here are meant to help give a better understanding of the inverse square law. This one, the point here is that the farther out you go, this is a automatic butter sprayer, patent pending, the farther out the distance is, which is represented down here, 3 times the distance, 2 times the distance, original distance, the thickness of the spray is decreasing from 1 millimeter to 1/4 millimeter to 1/9 of a millimeter. So it's decreasing at an exponential rate the farther out the distance, the farther out the bread is from the butter sprayer. This slide just kind of recaps that, so if any of this is a little confusing to you, that's okay. Just take a few minutes to go back over these slides and take a look at the book as well, and come into class with questions. And yet another way to represent this, showing this graph, the closer you get to Earth, the greater the force, the farther away the distance drops, but it doesn't drop in a straight line, it drops in this red exponential curve. The farther out, the more dramatic the drop in gravitational force. And again, that's due to the inverse square law. The fact that the denominator is squared in the formula for universal gravitation. The fact that it's over the distance squared. The farther the distance, the greater the drop, exponentially greater the drop in force. One thing that has puzzled great minds throughout recorded history is the idea of force acting at a distance. The idea that the Earth and the Moon have some kind of force between them that can't be seen or touched. Now, the idea of a force field or gravitational field says that the Earth is in contact with a gravitational force field and the Moon is in contact with the gravitational force field. So the Earth and the Moon are connected through this force field. A gravitational field is a type of force field, and a gravitational field, which is needed in your notes, occupies the space surrounding any massive body. There is a gravitational field around it. The lines represent the gravitational field about the Earth, and that's pointing in at all points around Earth. This represents the gravitational field around the Earth. Now, the next slides require a little imagination. There's some thought experiments that show what would happen if there was a hole bored through the Earth and you were to fall through it. As you fall and get closer to the center, there's actually a gravitational pull above you and below you, so that when you get to the center of the Earth, the gravitational field cancels itself out, and you would not be accelerating at all. You would, however, overshoot this, then start going out the other side, and eventually you would be gaining acceleration and then losing acceleration as you get closer to the surface and then start falling back toward the center. It's been calculated this trip would take about 45 minutes, regardless of your mass, because remember, things fall at the same speed regardless of their mass. This is a little thought experiment. Don't expect you to get this the first time you hear it, but it is something interesting to sit and ponder while you're sitting at home looking for something to do. You can start thinking about this. And if you were able to go into a cavity in the center of Earth, your weight would be exactly 0 because you would be pulled in all directions at once. Again, hypothetical thought experiment, can't really go there, it's kind of hot, kind of dense. Now remember that your weight, how many newtons you weigh, your weight in newtons is equal to your mass multiplied by the acceleration due to gravity. And 1 kilogram, a 1 kilogram mass, if you multiply that by the force of gravity, which is 10 meters per second squared comes out to be 10 newtons. So if you have something measured in newtons and you divide it by 10 or 9.8, you get the mass. So weight is measured in newtons and is a product of mass multiplied by gravity. Weight is relative, mass is not. The next slide gets into that. Now, if something happens that increases the support force from the floor you're standing on, then that would cause you to be heavier. If something were to decrease the support force, then you would be lighter. Your mass would stay the same, your weight would change. So let's look at that in terms of a person on an elevator. Let's say you're in an elevator and you're standing on a scale. Next time you go to the mall or go to a hotel somewhere, bring a scale with you, put it on the elevator. As the elevator goes up, that causes you to exert a greater force on the scale exerts a greater force on you, your weight goes up while the elevator is accelerating upwards. As the elevator starts to move down, it accelerates for a little bit downward. As it's accelerating downward, this is causing the scale to move away, to move down at the same time that you're applying a force down to it. This ends up causing the force you're applying to the scale to be less than your weight, and the support force to be less. Now, if the cable were to break and the elevator were to fall, you wouldn't be able to apply any force to the scale because you would be falling and the scale would be falling, and therefore your weight would be zero during that time. Your mass would be the same, but it would be impossible to apply any force to the scale since you're both falling through space at the same rate. So, when you see astronauts in outer space or on a space shuttle and they appear to be floating around weightless, they are in fact experiencing weightlessness, but they are not outside of gravity. You can never be outside of gravity. They are still pretty close to Earth compared to other things in space. Gravity is still a significant factor at that distance. The reason that they experience weightlessness is because since they are falling around the Earth, just like how the moon is falling around Earth, there's nothing for them to exert a force on, and therefore no support force back on them. They're falling, the space shuttle's falling, everything is falling. So there's nothing there to supply that support force to them. So they experience weightlessness because of the absence of a support force, not because they're beyond gravity. All right, in these pictures, each of these people are falling. One's falling and he's in outer space. The other one's falling and he's much closer to the surface of Earth. They're both going to experience weightlessness. Now, the person in outer space is not going to have the frame of reference to see how fast he's going as much as the person on Earth because he's not falling through air and particles and past other objects that are real close to him. He's in space. So, but they're both falling. They're both subject to acceleration due to gravity. They're both going to experience weightlessness. The reason is there's no support force back on them because there's nothing that they can apply a force to. The seat's falling, the astronaut's falling, the vehicle's falling, the person's falling. There's no support force back on them, so they are experiencing weightlessness. They're not beyond gravity. They're experiencing weightlessness because of a lack of a support force. And lastly, this law of universal gravitation is a major reason for success of science in explaining how the world works. Not only in explaining how we can launch stuff into outer space, how stuff moves around, but it also shows that there might be other equally simple laws that can help us understand the universe. If any of this was confusing, which it probably was, there's nothing wrong with that. Go back, take a second look at it, come in and ask questions, look in your book, look up other sources, and may the force, or rather mass times acceleration, be with you.